All right, y'all. Are you excited? I'm excited. Maybe I'm a little too excited. Maybe I'm too excited. But, guys, it's our first, kinematics problem. Our first, real physics problem. And it's a rocket sled. Can't beat that. A rocket sled starts at rest, speeds up in the negative direction. If the magnitude of acceleration of the sled is ax, what is the final velocity of the sled after t seconds? Oh, where are the numbers? Oh, okay. Anyway, they're not there, guys. Ax, t, what are we trying to solve for? Remember, this is way back when we're talking about units. Okay, if we have a rocket sled, speeds up in the negative direction. This is my negative direction. There it is, starts at rest. That's the motion right there. Okay, set. Okay, very good. That's the motion we see, right? And this is what's in words. So when you read that, that's what you should be imagining in your mind, right? And what it's saying is if the magnitude of the acceleration is a, we know the acceleration of this cart. We want to know what is the final velocity of the sled after t seconds, right? So where is it when I'm over here, right? Or over here, or however many seconds, okay? We solve this generally so that I can then put in any time in any acceleration to solve for what your final velocity would be. And you'll see this, okay? Okay, so picture. First thing we do, provide that picture. I've kind of provided a few pieces here. We'll do this together here, right? You need to label these, but we'll label it together. All right, so position x1. Which of these is going to be x1? The one on the left, one on the right? One on the right. Why is that the right one? Because I'm moving in the negative direction, which means you're moving left. So the dot to the left is going to be your second position, your final position. Each of these, let's see, I start at rest. So will I have a velocity at x1? The answer is no, I will not. But I will have a velocity at x2. What direction? It's going to the left, right? How big? I don't know. It could be this big, could be that big. Depends on how much time has passed, right? But I'll just put it this big, right? It's bigger than what it was, so that kind of makes sense to me. And I'll write v1 equals 0 here. Usually this right here, this is where I put the x equals 0 position. Okay. Graph. All right, typically only one or two need to be drawn in order to answer the question. Recognizing which graph to draw comes with good time and practice. On the graphs, first draw the beginning and end points. Then we fill in the expected pattern between those points. Acceleration will always be a horizontal flat line. Aha! Ooh, that's a big key right there. Pay attention to that one, right? Acceleration is always going to be a horizontal flat line, right? It might be positive, it might be negative, it might be 0, but those are the only 3 options for acceleration. Velocity will always be a straight line, right? We are going to assume always a constant acceleration if we have acceleration. So my velocity lines will always be straight. All right, position could be a line or a curve, right? It's a straight line when velocity is constant. It's curvy when you're either speeding up or slowing down, right? Usually we don't draw it. I'm going to draw it in this one instance because after we go through the graph method, I'm going to come back and I'll show you the table method, though, in case you didn't go through the PowerPoint. All right, now I'm going to, let's say we didn't have my nice Logger Pro. You'll see that in a second. We'll see my Logger Pro. We'll verify and see if we're right on these. But if I didn't have that, as long as my picture's right, how can I get this? Well, what does it say? It says, draw the beginning and the end points. So let's start with velocity. I'll make velocity blue. All right, start with velocity. At time, t is 0. What is your velocity? So at position x1 or velocity v1, your velocity is 0. Right? It's very clear right there. Right there, 0. You don't have to draw this, right? I'm just drawing it to make a point, right? 0. That's how you put that on the graph. T equals 0, V equals 0, 0, 0, right there. Now, at some later time, right, I could use this point, that point, that point. I'm just going to use the end of the graph. I'm going to say this right here, this is T. whatever time I'm trying to figure out. That one right there. Okay. After that point, at x2, right, how would I describe my velocity? Well, my velocity is it positive or negative or 0? It's pointing to the left, that would make it negative. Okay, so it's some negative number that's bigger than 0. There you go. That's it. Connect them with a straight line. And that's it. That's it, guys. All right. I didn't have to do that first, but I did do that first, right? From velocity, I should be able to get both my position and acceleration graphs. Let's go to acceleration first. You remember what that relationship is? Acceleration is the blank of velocity time graph. Hopefully your blank is slope. Yes, slope, slope, slope. The slope of velocity tells you information about your acceleration. I'll make acceleration red. How would you describe your slope? Slope is, it is downward, but I wouldn't say downward. I would stick with positive, negative, 0. Acceleration is negative, right? It's negative because it's going downwards, right? Downwards, negative, right? And it's always a flat line, right? That star right there, always flat line. You just have to say positive, negative, 0. There you go. The other way I could have known that my acceleration was negative is if you're moving in the negative direction and you're speeding up. What does that tell you about acceleration and velocity? They must be in the same direction. So if velocity and acceleration are in the same direction, you speed up. If you're speeding up, velocity is negative, acceleration must be negative. Okay, now last one here, brown. Position. Where do I start in terms of my position? I start at 0, right? Start at 0. And I end somewhere over here. That's some negative number, right? Some negative number. Now there's really 3 ways that I could get there, right? I could do straight line. I could do curvy like so. Or I could do curvy like so, right? One of those absolutely gone, right? What does it mean to be going in a straight line for position time? It means you are at constant velocity. Was that thing moving at constant velocity? Nope. So straight line is gone. Gone, gone, gone. Okay, where are you? There we are. Oh, nope. Erase, erase. So now here we go. So now we have to think about what's going on with these 2 curvy things here. Both of them seem to have negative slopes, so that's okay. But which one? Well, let's see. My velocity is increasing. How do I get velocity from position time? From position time graph, the slope tells me about my velocity. So if my velocity gets bigger as time goes on, let's insert that, copy, paste. The slope gets bigger as time goes on. Does the top or bottom brown line have a increasing slope as time goes on? Hopefully you said the top one, right? There you go. Slow, 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 fast, 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 and there you go. All right, so that's what all these graphs look like. You want to confirm? We can confirm that too, right? I'm going to clear this. Oh, well, actually, maybe I won't clear it yet. Let's see if I could do this. Hey, nope, didn't do that. One moment. There we are. Let's get this. Okay, I'm gonna all clear. Need to click over here. All right, a little short. Ooh, kept going there. Let me do it one more time. I'll use a little bit of a slower one. Oh no! All right, there we go. Now, I might be worried there for a second, but I'm going to do Command-Z and bring that guy back. There he is. So, I know all my graphs are gone, but we can see there's my position. It looks just like what we expected. Here's my velocity, velocity 2, pretty much just as we expected, right? Here you're at rest, and then I let it go, and there it is. And then I stop it right there. So this is the area that we're really interested in. And then what does your acceleration look like? Acceleration looks in that same region, pretty much negative, constant as we've seen before, right? So everything there seems to check out just fine. Let's go back to position 2 for now. Right, notice I didn't quite start at 0, 0, but that's okay. All right, let's come back over here. Let me bring this, and then I will come over here, go like this. All right, wonderful. So everything checked out. Everything checks out in regards, now we have our data ready to go to. All right, text. So from the graphs, we're gonna build our equations, right? We're gonna focus on area, right? If we focus on the line, that's really the table method. I'll show you here in a second, but we'll focus on area. Remember, area of a velocity time graph is displacement. Area of the acceleration time graph is, don't just say velocity, right? You gotta have two words in front of that. Change in velocity, right? How much your velocity changes. That's the area of the acceleration time graph. Displacement, just like displacement is your delta x. How much does your position change, right? The areas that we're gonna work with are triangles and rectangles or squares, right? But we're not talking about rocket science here. We're just doing our 1/2 base times height or our just plain old base times height. We're going to write down the equations in symbolic form, right? I can hear the groaning through the internet ether, okay? I understand, right? But this is just part of what it means to be a physicist. You have to be able to talk about things in symbolic form, right? We're going to use algebra to solve for the unknown, and then we're going to apply it to the demo. Then you're going to be able to punch in some numbers, right? But hopefully, when we go through and apply this multiple ways to the demonstration, you'll be able to see, oh, okay, this is what I'm doing when I'm solving this problem, right? I'm not just plugging numbers in and getting something, like I'm calculating something real, something tangible, right? Something where you can measure it and you will actually be able to guess very well, like better than it really has any business to do, right? It's quite cool, quite mysterious, but I won't quite go down that philosophical lane right now. All right, velocity looked like that. Acceleration, I'll use a different color. Nope, that's the same color. Looks like this. All right, so now when you're going through this process, right, sometimes you have to use both graphs. Sometimes you just have to use one. When you're just going through the process, I just say go through the whole thing, right? Just go through this whole process, and then in the end, we'll ask ourselves, what the heck was I trying to solve for in the first place, and go from there. Area of the velocity time is my displacement. So how do we calculate my displacement? Delta x is equal to the area, which is 1/2, because it's a triangle, times base, which is time, times the, I'm going to write this as delta v, right? That's the change in velocity. I always write it as delta v. Even if 1 is 0, I always write it as delta v. You'll see why. Okay, so this is my displacement equals 1/2 t times delta v. Now I come over here to the acceleration. Bump, bump, bump. Here we are. Acceleration is change in v. There we go. Then I end up my delta v is equal to, well, base times height. That is time. Height is acceleration. And then I get a times t. Notice that this here is the fundamental equation for acceleration. Acceleration is equal to delta v over t. Right. From here, we go back to, like, what are we trying to solve for? What is it that we are really trying to solve for? Well, it was my final velocity, which is my change in v, right? I want to know what's my change in v. Notice that is in both, right? I could use, it's there and it's there. I could use both to solve for this. So if I go through this in a very systematic way, right? I can say, well, I know how much the time is. I know the value of a half, but I do not know what my displacement is. It doesn't tell me what my displacement is, right? It wants to know, well, what's the final velocity, right? It's not saying what's your final displacement. I could solve for that if I wanted to, but that's not what I'm trying to get at. Okay, so I cannot quite use this to solve for it yet, unless I could somehow calculate delta x. So we go to the other graph. We go to the other equations, because I can solve for delta v there too. Now, go through the same thing. I know the value of acceleration. How do you know it, Dr. Ray? It says, right? You have an acceleration value a, right? And it wants to know after how much time. All right, okay. So if given time, given acceleration, I can calculate what my change in velocity is. Technically, right, that v2 is what I'm solving for. Minus v1 is equal to a times t, but v1 is equal to 0. Right, so v2 is then equal to acceleration times time. Now here's where we want to apply that to the demonstration. So let's get back. So what do I need from here, right? What do I need from this little piece? I need to know what my acceleration is. How would I get that from here, right? Well, I could do that two ways, right? And I will do that two ways. I'll get from velocity, right? If I highlight this is my velocity, I can get linear slope right there. It says my acceleration is negative 0.2778, right? Likewise, I could go to acceleration itself, and I could do statistics. Statistics, let's see, mean value, negative 0.28, so about 2.8. So we'll deal with that. We'll take that as what my acceleration is. So let me clear all these, right? Hey, that's not what I wanted to do. There we are. Who keeps doing that? I don't know what's going on. All right, I wonder if it's gonna let me do it now. Draw. Nope, it doesn't like that at all. Okay, I get you. Sorry guys, this is the first time that's happened. I'm going to do this. Thank you for your patience, everyone. Okay. Well, I won't be doing that anymore. Guess I'll just have to go back and forth without having them side to side. A equals VT. Oh. V2 equals A times T. I know my acceleration is about negative 0.28 meters per second squared. And then we could just pick a time, right? How much time went by when I was doing this, right? Well, I'm gonna go to the velocity, V2, right? About here. Clear that. Let's go to the examine. Right there is kind of where I start moving. So I start moving at about 0.60 seconds, right? So draw, right? T1 is equal to 0.60 seconds. And let's just say I want to know speed at 2 seconds. 2 seconds right there. So say T2 is equal to 2 seconds. What's your speed at 2 seconds? But we got to be careful because on here, my speed actually started at 0.60. So that means my delta t, how much time has passed, has been 1.40 seconds, right? When you do your problems, it's not going to be as complicated because it would actually start at 0, right? Time t equals 0. But our time is 1.4 seconds. So if I pull this through, right? Let's see. 0.28 negative times 1.4 is equal to negative 0.392. And so if I come up at 2 seconds, oh man, look at that right there. Velocity negative 0.390. Dang. See, that's what you're doing, right? I could do this for all, let's go for 3 seconds, right? This is the benefit of having 3 seconds. Or doing this generally, right? Now that I've done this, I'll say T2 is 3 seconds, which means my delta t is now 2.40 seconds. All right, clear this. I'll take 0.28 negative times 2.40 seconds. So at 3 seconds, I should be at negative 6.72. It's so close, right? I'm just off by 0.05 seconds, 0.05, right? But guys, I mean, that's how close this is. This is pretty cool. This is really pretty cool. I'm just gonna say that. I'll say that again a lot, guys. It's cool stuff. But this is what you're doing, right? When you're calculating these things, like, this is the real data. This is the real data. This is not some sort of like made up question about a cheetah or a rocket sled, right? This is real life. This is data, and this is the equations that come from just what we did based on how the graphs look, right? If that doesn't catch your fancy, if that doesn't catch your curiosity, if that doesn't make you think that's a little cool, we're in for a long semester, guys. Okay, here we go. So when you go and you applied it to the demonstration, now same problem with numbers, right? Same problem with numbers. Y'all just get to do that one on your own, but hopefully now you have a better idea of what's going on when you're actually solving these. After you're done plugging that in, I'm going to run through this with the table method really, really super fast, right? So if you're done, you're done. That's great. Move on to the next one. If you want to see how this goes, perfect. Okay, so what happens here is we have this, and then we have this right here. So the table method, what the table method does here is it takes the actual line. So instead of doing the area, it does the line. All right, I'm going to do this over here. So for velocity, right, you have equation of a line. Equation of line, right? What's the equation of a line, right? Y equals mx plus b. What's on the y? Well, that's your final velocity, right? So you final velocity, v2, is equal to, well, what's your slope? We know what the slope is. That's your acceleration. Acceleration. What's on the x-axis? Well, that's your time. So vf equals at, and then your y-intercept would be, in this case, 0, but it doesn't have to be 0. Y-intercept would be your initial. vf equals at plus vi. Move things around. vf, come on. Erase. VF minus VI equals AT divided by T. A equals delta V over delta T, right? It's the same way of getting to the same equation, guys. That's all I'm trying to say there. The acceleration one doesn't tell you a whole lot. This is just acceleration equals acceleration. It's just a constant, right? So you get VF squared, VF minus VI is equal to AT. Now for this is a line, but this is quadratic. It's a quadratic line, right? We're going to be doing this in lab 2, guys, right? Quadratic line equation is y equals 1/2. It's not 1/2, sorry. It's not 1/2, right? It's just ax squared plus bx plus c, right? How does that translate to what's going on? We have final position, that's what's on the y-axis. This a coefficient right here just happens to be 1/2 of the actual acceleration. A, in this case, is just some number. Over here in the actual equation, it means acceleration. X-axis is t, 1/2 a t squared, plus b, that's your initial right here. So this is initial position, or initial velocity, sorry, v1t plus x0. So c was the initial position, and that b right there happens to be your initial position, velocity. Initial velocity. B is the initial velocity, right? So that's just, it comes from modeling, right? And you'll model that when we get to projectile motion in lab, okay? So that's where that comes from. You take these two equations and you put them together and you get one where you can get vf squared equals vi squared plus 2a be x2 minus x1. This is algebra, right? By doing two equations, two unknowns. Who's missing in there? Mr. Time is. So you take away that time, eliminate it, and you end up with this nice little algebraic solution. And so these are your basic equations, but it comes from the lines. So you start with these equations, you'd be like, okay, what am I trying to solve for? Trying to solve for this VF right there, VF right there, right? I know V1, I know V1, right? Let's see, VF is not in here. Let's see, so can't use that one. All right, not very linear process going on here. It can be much more linear if you actually look at that. What would that be? The thing I talked about earlier that talks about using the table method. It's in the additional learning supplements, etc., etc. Let's see. This one can't work because we don't know what that displacement is, and so we're back up to using this one. And guess what? We end up with the exact same solution we had when we did the area method, right? Which is kind of neat. Kind of neat. But like I said I was going to do that. That's going to be the one time I do it. The rest of it is going to be using graph method, and that is the method that I hope you all start to use, because you just I think you get more out of it in regards to knowing what's going on, in regards to physical thing moving. All right, let's get moving ourselves onward to the next round.